Alrighty, so this video we're going to work some example problems for the heat transfer method of conduction. In the previous video, in the lecture, we found the big equation we're going to use is the heat transfer rate, Q over T, so that's how much energy is transferred per second, is equal to K, the conductivity, A, the surface area, how big is the object that the heat is trying to go through, delta T, which is the difference in temperatures from one side of the object to the other, divided by L, which is the thickness. How thick is the material you're trying to pass the energy through? And what we found is we can basically ask a couple of different types of questions. One is, what is the heat transfer rate, or how much energy per second is passed through this particular object if the temperature on one side is this and the temperature on the other is that. The other way we can ask it would rewrite this equation by asking how much energy is transferred through this object in 10 minutes or 5 hours or something like that. For that, you would just take the exact same equation, K, A, delta T over L, and you just bring the little t for time to the other side. And so if you want to know how much energy is transferred in 5 hours, little t would be 5 hours. Of course, you would convert that to seconds, so multiply by 3,600 seconds, and then you'd find out how much energy is transferred in those 5 hours rather than per second. So really easy manipulation. And so now what we want to do is do a couple of examples. So let's take the first example, and for this one we will say, how about this, a little something new. You have a metal cylinder whose diameter is 5 centimeters and is, let's say, 50 centimeters long. You know its conductivity is 300. If the temperature on the left face is 200 degrees Celsius, and on the right is, let's say, 10 degrees Celsius, find the heat transfer rate through the metal. Okay. So first thing I'm going to do is go ahead and draw it out so we could see what this looks like. So here's a little metal cylinder. Okay. I know that the length of this cylinder is 50 centimeters, so that's 0.5 meters long. And I know that the diameter of the face is 5 centimeters, so that's 0.05 meters. I know the temperature is 300, I'm sorry. Let me go ahead and rewrite it over here, get it out the way a little bit. The temperature on the left face is 200 degrees, whereas the temperature on the right face is 10 degrees. And I'd like to calculate the heat transfer rate. So, I know the equation, Q over T is K A delta T over L. So all I need is the conductivity, K. Do I know that? Yes, conductivity, 300, I'm sorry. I need A, the surface area. So that's how big is the face that this heat is trying to pass through. Well, for a cylinder, the face is a circle, right? The left side, if you look at it face on, it's a circle. And so I need the area of that circle. Well, I know the area of a circle is pi times the radius squared. So for us, we don't know the radius, but we know the diameter. So we could use the other equation, which is pi d squared over 4. It's basically the same as get the diameter, divide it by 2, now you have the radius. It's just, you could write it like this as well. It's exactly the same thing. So if we do it, we get pi times 0.05 squared over 4. I stick this into my calculator. 0.05 squared times pi over 4. And I get 0.00196. Okay, so now I know the area. Delta T, I need the temperature on one side and the temperature on the other. I subtract them. I know that. And I need L, the thickness. Well, the thickness is the length of this cylinder, right? The energy has to pass through this thing, and so the thickness is the length of the cylinder. So I know everything. I know all the numbers now that I've calculated area. So I just plug them in. 300 times 0.00196 times T1, 200, minus T2 is 10, all divided by the thickness. The thickness is 0.5. So I want to stick this into my calculator. I get 223.8 joules per second. And that's how this kind of question goes. And any question like this. In the lecture video, we had a square window or rectangular window. This time we have a cylinder. It's done the same way. The difference between those two problems was the fact that to calculate the area of a cylinder, or at least the face of a cylinder, we had to know area is pi r squared. To calculate the area for a rectangular window, it's length times width. But everything else is the same. It's the same equation, and we're plugging the numbers in, and we're getting our answer. So just be sure when you're reading these questions that you understand the shape of the object, because the shape of the object will dictate how you calculate its area. Now, let's try another example. Let's say a window of conductivity 100 has dimensions of 2 by 3 by 0.1. So that is, let's say 2 length times width times height. It's length of 2, width of 3, and then the thickness is 0.1. All right, so we have this window. We know a little bit about it. If the temperature on the outside face is, let's say, 40 degrees Celsius, and the temp inside is 20 degrees Celsius, calculate how much energy is transferred into the room in 1 day. All right. So I'm going to go ahead and draw this out. The way I'm going to draw it is we're going to look at it from the side view. Okay? So as if we're looking, you know, from inside the wall at the edge of the window. And so that's going to look like this. Here's the edge of the window. This is the outside over here. T out is 40 degrees. T in is 20 degrees. The thickness is 0.1. And then we have the dimensions. So for instance, it could be look like, you know, the dimensions are this way, say 2, and this way 3. And I want to know how much energy is transferred in 1 day. So that's going to be Q equals K A delta T over L times little t. So what do I need? I need K. Do I know K? Yes. K, that is the 100. I need A. Well, I can calculate that from 2 by 3. I need the temperatures, 40 and 20. I need the thickness, that's the 0.1. And then I need time, which is 1 day. But remember, our normal units have to be seconds for time. So I need to calculate 1 day is how many seconds. So to do it, I need to convert. Let's say in 1 day, there's 24 hours. And then in 1 hour, there's 3,600 seconds. And so if we do this calculation, we'll get how many seconds are in 1 day. So 24 times 3,600 gives us 86,400 seconds. And now I have my time. So now I can plug my numbers in. 100, the area is 2 times 3, which of course is 6. Delta T, 40 minus 20. Thickness, 0.1 times the time, 86,400. Again, I plug all this stuff in. And I get a really big number, 1.04 times 10 to the 10 joules. Too many decimal places, I had to use scientific notation. But there we go. So, for a window of this size, on a nice hot summer day, it would let in all of this energy. All right, so we've seen the difference here. We have a cylindrical object, so the surface area was calculated using pi r squared, and we want the heat transfer rate. Here, we have a rectangular object, so the area is length times width. And instead of the heat transfer rate, Q over T, we just want to know Q, how much energy in a certain period of time. So the only difference is, of course, we move the T over to the other side, and now we calculate the total energy. I want to do one more example, which shows a more complicated setup. But we're going to find that for this particular type of problem, we're basically going to do the same thing, except we're going to have to do it more than one time. And so here we have the problem of a double layer system. So let's say I've got two layers. Here's one. And here's another. We've got K for the first layer is 300. K for the second layer is 200. The area for the first layer, let's say, is 10. The area for the second layer is also 10. They're the same size. The thickness of the first layer is 0.5, so 50 centimeters, whereas the thickness for the second, let's say, is 0.2. So the second layer is not quite as thick. It's a thinner material, but it's made of a different conductivity, so a different material. If I know that the temperature out here is 100, whereas the temperature over here is, let's say, 20, what I would like to do is find A, the temperature between the layers, and B, the heat transfer level, heat transfer rate through the system. So, definitely we have a problem that looks different. We're still talking about conductivity. We still have some material. We're trying to pass energy through this material from the hot to the cold. However, now, instead of it just being one single piece of material, our system is made of two different things, kind of touching each other and sandwiched with each other. And so maybe this is like, a wall and insulation, or a window and drapes, things like this. Or, it could be your body and a shirt over your body. So you're trying to pass the energy through this object, but it's made of multiple materials. So let's think, how can we possibly solve this type of problem? Because what I'd like to do is use our normal equation, Q over T is Ka delta T over L, to try to find, let's say, part B. I want the heat transfer rate. But how do I do it if I have two materials? Because each material can have a different K value. It can have a different thickness. It can have a different area. So what do I do? Of course, there's multiple ways I can try doing it. I can, one thing that comes to mind immediately is, well, do this equation for the first layer and get a number, and then do the same equation for the second layer with his numbers and get a number, and add the numbers together. That's one possible way of handling it, but that's not the right way. The way I want you to think about this is, let's use a little intuition, and I'm going to show you something from a different field of physics that relates to this. Think about pipes with water. So let's say I have a pipe with some water in it, and that water is flowing through the pipe. Okay? Well, one thing you will find when we get to fluids is that water flowing through a pipe moves at a certain speed, and the speed can change depending on how big your pipe is. If you don't believe me, think about, we've all done it. You get a hose in your backyard, you've got the hose attached to the spigot, you turn it on, the water's coming out. But then you put your thumb over the end, which basically makes the hole very small, and what happens? The water shoots out a lot further. It's coming out a lot faster. And the reason is because the way fluids work is if you constrict the opening, the fluid increases its speed. Okay? And there's a certain reason for this. Let's look at it. Why would this happen? Well, think about it this way. If I were to take a pipe and I constrict a pipe like this, and you have a whole bunch of water flowing through, it gets to this constriction point, and what's going to happen? Well, there's two things that can happen. The first thing is nothing special. Water's flowing in, it wants to flow out. If it's all at the same speed, then there's a whole lot more water trying to come in to the constriction than can come out. And what would eventually happen is you get a big old buildup of water at the constriction because it can't get out fast enough. It's coming in too fast and not enough can leave. You get a buildup of water and the pipe bursts. But thankfully, that's not how it works, because every one of our houses or apartments, all the pipes would be bursting all the time, because the way we try to regulate water getting to different parts of our house, whether it's upstairs, downstairs, coming out of our shower head, whatever, is we use different size pipes. Instead, what happens is when the water tries to feed through this constriction, in order to allow all the water that's coming in to leave, the water speeds up when it goes through the constriction. And it speeds up in such a way as the total amount of water out is equal to the total amount of water in. So if you have a gallon of water coming in per second, then you better have a gallon of water going out per second. Because this side of the pipe is really, really big, you have a heck of a lot of water going through this opening. And since this side of the pipe is really small, if you need that same amount of water to come in per second, or to go out per second, it must be moving a lot faster to keep up with the intake. And so in fluids, this is called the mass flow rate, or the volume flow rate. The amount of water coming in per second must be the same as going out per second. Well, with that, let's look at our heat. Heat is trying to flow through this first piece of material. So it's moving through, and it's moving through at a certain rate called Q over T. Then it hits the second material. Well, let's pretend like the second material is harder to move through. It's a lower conductivity. Well, if the heat is coming in at a certain rate and it's trying to leave at a lower rate, then obviously you'll get a build-up of heat at the interface between the two layers. And if that happens, if you have a heat build-up, that means either the material is going to melt, it's going to explode, something like that. So instead, as the heat tries to pass through this system, because maybe the right side is more difficult than the left, everything is slowed down so that the original intake of this heat will be less from the very beginning to accommodate for the fact that the heat can't get through fast enough. And the way we say it is the heat transfer rate through the first material, Q over T, for the first material is the same as the heat transfer rate for the second material. That's like the volume of the water coming in is the same as the volume of the water coming out of our pipe. The heat coming in, the rate of the heat coming in is the same as the rate of the heat going out. Okay? And we're going to use this fact to let us solve for this problem. But in order to do it, notice what I have to do. If I'm going to do, let's say, Q over T1, what do I need? I need is K. Well, I know that. That's fine. I need is A. Well, I know is A. That's 10. And I need delta T. But notice what delta T is. Delta T for the first material is this side of the material and this side of the material. I'm not looking over there on the right because that's material 2 stuff. So I need T1, but I also need this other temperature. I'm going to call it T3. This temperature that's in the middle here. But I don't know it. It's not given in a problem. That's why I arranged this problem part A to force you to find what this number is. Because once I know that number, I can get Q over T1. And of course, Q over T1 is the same as Q over T2, so that is the heat transfer rate. I'd know part B immediately. So that's what we're going to do. Let's look at part A. I need to find this T3. I can't do it with just one of these Q over T's because it's the unknown. And I also don't know what Q over T is as a number yet. But what I'm going to say is that Q over T for material 1 is equal to Q over T for material 2. Well, what is Q over T for material 1? K1, A1, delta T1 over L1. And the same for 2. K2, A2, delta T2 over L2. And now plug the numbers in. K1, that's 300. A1 is 10. Delta T1, I'm going to use left minus right. So T1 is 100 minus the right side of material 1 is T3. I don't know the number, but that's what I'm looking for. Divided by L1, the thickness is 0.5. What about for 2? K2 is 200. Area 2 is also 10. Delta T2, remember I'm doing left minus right. So the left side of material 2 is T3 minus the right side of material 2, which is T2, 20. And all that divided by L2, which is 0.2. And now when you look at this equation, notice there's only one unknown, T3, which is exactly what I'm trying to find for part A. The key is, number 1, knowing that if you have a double layer system or an infinitely layered system, multi-layer system, doesn't matter, the heat transfer rate through any one material, any one of the layers, is the same for all of the layers. So I just equate them. Q over T1 is Q over T2, and I plug my numbers. The important thing to not mistake is that when you're doing delta T, whatever way you do it for the first layer, you do the same for the second. So for me, I did left side minus right side. And because I did that for the first one, I have to do left minus right for the second as well. Don't switch it and do right minus left. Now, if you did the first one right minus left, then the second one would have to do right minus left as well. As long as whatever you chose for one, you do for the other, you're good. All right, so Now I need to go ahead and get this all together. So I have 300 times 10. I'm cross multiplying. 0.5 goes over there, 0.2 goes over there, basically. Times 100 minus T3 times 0.2 equals 200 times 10 times T3 minus 20 times 0.5. All right, so what is all of this? 300 times 10 is 3,000 times 100, okay, minus, I'm sorry, times 0.2. I'm forgetting that. So we do 300 times 10 times 100 times 0.2, right? This times, oops. This times this times this times this. Distribute it all. This gives me 60,000. Then I do 300 times 10 times minus T3 times 0.2. So 300 times 10 times 0.2 times minus 3 is minus 600 T3. And now we do the same on the right. I've got 200 times 10 times T3 times 0.5, which is 1,000 times T3, minus 200 times 10 times minus 20 times 0.5, which gives me 20,000. All right, so now what do? Collect all the T3 terms on one side, all the numbers on the other. So this gives me 40,000, I'm sorry, 80,000. What am I thinking? 80,000 on the left equals 1,600 T3 on the right. Divide the 80,000 by 1,600, and I get T3 is 50 degrees. And that gives me my answer for part A. Could this be right or could it be wrong? Do I have a way of checking it to see if it makes sense? I can. Look at the original picture. The left side is hot at 100 degrees. The right side is getting colder and colder until it gets down to 20. So in the middle at T3, it has to be somewhere between 20 and 100. Just intuitively. Here I get an answer of 50. That's between 20 and 100. So it looks good to me. If in calculating this I get an answer like 500, then I know it must be wrong. It doesn't make sense. How can the middle be hotter than the hot side of the material? And of course, the same could be said if I got a negative 50 as my answer. Well, that can't be right either, because the colder this whole material gets is 20 degrees, which is on the right. So my answer has to be somewhere between 20 and 100 for this problem. I got 50. Nothing's wrong there for me to see, so it must be okay. Now what about part B, the heat transfer rate through the system? Well, all I have to do is either find Q over T1 or Q over T2. Either one will do it. So just pick one. It doesn't matter what you pick. Let me pick Q over T1. Q over T1 equals K1, 300, A1, 10, delta T1, 100 minus T3, but I now know what T3 is. It's 50, divided by L1, 0.5. And now all I have to do is plug these numbers in to my calculator, and I'll get my answer. Here I get 300,000 joules per second. Now, a way you can check this answer to see if this is true is find Q over T2. Q over T2, if I were to calculate that, better be the same as Q over T1. And of course it is, if you plug the numbers in. 200 times 10 times 50 minus 20, that's T3 minus 20, over L2 of 0.2. You plug that in, you get the same answer. So that's good. It better come out to be the same. If it didn't come out to be the same, then somewhere you did a calculator mistake. Because the fact that you used the fact that they're equal to get T3 better mean when you find them, they are indeed equal. But this is a multi-layer system. This is as complicated as these are going to get. They can't be more complicated than this. Most of the problems you have will be like these. A single layer, you're finding a heat transfer rate, or you're finding how much energy flows in a certain period of time. But this is available too. You have 2 different materials or 3 different materials, however you want to do it. We're allowing the heat to transfer through this system. First thing you should do is calculate the energy in the middle, the energy at the interface between the 2 materials. Call it T3 or call it T middle, whatever you want to name that value. I usually call it T3, but that's just, my own thing I've been doing since I learned this and when I was a student. So first you calculate that. Once you've calculated that, thankfully, the heat transfer rate of the whole complicated system, no matter how many layers it is, all you have to do is calculate one of the layers. So pick 1 or pick 2, it doesn't matter which you pick, and then use the T3 you just found to calculate the heat transfer rate for that. Once you find it for one of the layers, that must be the rate for the whole dang thing. So anyway, these were some examples for conduction. Pretty much any problem I give you will be something like one of these 3. So I hope this is helpful in you practicing the problems. And of course, as always, if you have any questions about any of these things, you see I did anything wrong, or you're confused about a step, please email me. I'll be happy to help to the best of my ability. But definitely practice and practice and practice these problems to make sure you understand where the numbers are coming from. Make sure that you can do, for instance, the algebra here, because of course it looks a little messy. You have denominators and all this stuff, but at its heart, you're just distributing the numbers through, so take your time with it. And if you practice enough, you'll be used to it, and you can pretty much make your own video working examples just off the top of your head. But anyway, until next time.